Hi, folks. We are starting section 6.2 today, which is orthogonal complements. Let's go ahead and get this underway. So the definition and the theorems we're working at today work for any subspace of Rn. We can start with any subspace. The orthogonal complement of W, and the notation for that is W with a little perpendicular sign above it, is the set of all the vectors in Rn that are orthogonal to the vectors in W. So on the next slide, we'll see an example of an orthogonal complement. Actually, the next slide after that, we'll see another example. But so that might help make this definition make sense. We're going to start with my W is going to be the span of the vector 1, 0. Now, that's definitely a subspace because all spans are subspaces. 1, 0 is just the E1 vector, and if I take all of the scalar multiples of E1, then I get all of the positive and negative multiples of E1, and so W is the entire x-axis. W contains all of the vectors on the x-axis. And if I take the vector 0, 1, which is this vector here, that vector is orthogonal to any vector that's on the x-axis. The length of the vector on the x-axis doesn't matter. As long as it's on the x-axis, it's going to be perpendicular to 0, 1. In fact, any vector on the y-axis is going to be perpendicular to any vector on the x-axis. So all of the vectors on the y-axis are in the perpendicular space to W, the orthogonal complement to W. So in 2 dimensions, the orthogonal complement to the x-axis is the y-axis. In 3 dimensions, the orthogonal complement to the x-axis is the entire YZ plane. All the vectors on the y-axis are perpendicular to the x-axis. All the vectors on the z-axis are perpendicular to the xw. And any combination of a y-coordinate and a z-coordinate. So if I have a, an axis in 3 dimensions, that axis goes perpendicular to an entire plane that's a wall at a right angle to that axis. All right, let's move on. We have a theorem here that says, again, this is true for any subspace, that the orthogonal complement contains a 0 vector. This is true because the 0 vector dot with anything is 0. So the 0 vector will always be in the orthogonal complement. And the orthogonal complement is also closed under addition and scalar multiplication. And therefore, the orthogonal complement is also a subspace. So W and the orthogonal complement of W are both subspaces. And because the orthogonal complement is also a subspace, it has a basis. We can write it as a span of a set of vectors. We can do the things with W complement that we can do with other subspaces. And so in the next example, we are going to, for right now, we're just going to set up the equations to find the subspace that we're looking for here, the orthogonal complement to the column space. In example 4, we'll go ahead and set up and solve some equations, but I just want to set them up for right now because there'll be a pattern that we're going to notice. All right. So we are looking at the orthogonal complement to the column space of A. So if a vector is a vector in the column space of A, then all of these statements must be true. that the dot product of v with 2, 5, 3 has to be 0, and the dot product of v with 7, 2, -1 has to be 0, and the dot product of v with -3, 0, 9 has to be 0. There's a dot here, it's just really hard to see. And the dot product of v with 1, 4, 0 has to be 0. All four of these statements have to be true. I'm going to repeat these statements on the next slide. So the dot product of v, and this is v here, it's just a vector x, y, z. Dot with each of these vectors is 0. But we can write that as a system of equations. The top left one says 2x plus 5y plus 3z is equal to 0. And then the second one says 7x plus 2y minus z is equal to 0. Third one says -3x plus 9z is equal to 0. And the last one says that x plus 4y is equal to 0. And I'm going to put these on the next slide. But I want to point out two things about this system that we have. One, all the right side is 0, so this is a homogeneous system. On the left side, these numbers, 2, 5, 3, 7, 2, -1, so on and so forth, are these numbers, but they're transposed. That is, the transpose of A is 2, 5, 3, 7, 2, -1, -3, 0, 9, 1, 4, 0. And so this is the homogeneous system of the transpose matrix, which is the null space of the transpose matrix. The null space is what we get when we solve the homogeneous system. And so we have a theorem about this that connects two concepts now. It connects the concept of being orthogonal and shows that that is the relationship between column spaces and null spaces. Is that there's a perpendicular relation to them. The column space of A, if we look at the orthogonal complement to the column space of A, it's the same thing as the null space that we get when we transpose A. And armed with this theorem, we can now solve this system here. A is this matrix here. We want to compute the column space of A perpendicular by the theorem. The column space of A, the orthogonal complement of the column space of A, is equal to the null space of A transpose. So A transpose is the vector matrix 1, 1, 0, 2, 3, 2. We'll augment that with zeros, make this a homogeneous system. And we'll solve this. We'll take row 2 minus 2 row 1. And we get 0, 1, 2, 0. And then we'll take row 1 minus row 2. And we'll get 1, 0, -2, 0, 0, 1, +2, 0. So these are the equations. X minus 2z equals 0, and y plus 2z is equal to 0, which we can rewrite as x is equal to 2t, y is equal to -2t, and z is equal to t. And so x, y, z is equal to t times a vector 2, -2, 1. And so the null space of AT, which is the same as the column space of A, the orthogonal complement of the column space of A, is the span of the vector 2, -2, 1. Now we have solved this problem. We're done with this problem. But if you wanted to check your answer, say you have an exam coming up, if you have an exam coming up and you want to test your answer, this vector here should be perpendicular to these vectors here. So we could take the dot product, 2, -2, 1, dot with 1, 1, 0, and 2, -2, 1, dot product with 2, 3, 2, and let's see what happens. On the left, we get 2 plus -2 plus 0, and that's 0, so these are perpendicular. Over here, we get 4 plus -6 plus 2, and that's also equals 0, and so that's perpendicular also. And so we not only can solve this example, but we can check our answer. All right. Well, thanks for sticking around. We will start section 6.3 in the next video. Take care.